Okay, in this video I'm going to talk about the Gergonne point of a triangle. So basically we have an arbitrary triangle and we consider the incircle in this triangle, which means the inscribed circle that touches all sides, and we consider the tangency points of this circle with the sides, and we connect these tangency points with the opposite vertices of the triangle, so like this and like this, and it turns out that these three segments intersect at a single point, and this point is called the Gergonne point of a triangle. So let's denote the so this is the triangle ABC, and we have the tangency point, denote them as TA, TB, and TC. And the theorem says that ATA, BTB, and CTC intersect at a single point, which is called the Gergonne. The Gergonne point of this triangle. I can write off the triangle ABC. Okay. So the proof is actually quite simple. Well, it's simple if we use the Cheo's theorem. So it's a simple corollary of the Cheo's theorem. So the Cheo's theorem is a criterion when exactly the three segments like this. So the segments connecting the or rather the lines connecting the vertices of the triangle with some points on the opposite sides or on the extensions of the opposite sides, and it says that so this is the Cheo's theorem. It says that AD, BD, BE, and CF intersect at a single point if and only if, well, for only if we need to state it more carefully, intersect at a single point, or all three are parallel to each other, or all three parallel to each other if and only if the following ratio, the following product of the ratios. So we start with some point and we go clockwise. So let's say BD over DC multiplied by CE over EA. It's the vectors here multiplied by, so the ratio is signed. It can be positive or negative depending if the vectors have the same direction or the opposite direction. AF over FB is equal to 1. So in our case, so this is the Chev's theorem. So in our case, let's turn back to this case. So we know that the tangents to the same circle from the same point are always equal to each other. So this segment, for example, is equal to this segment, right? So like if you draw here any circle and we have from some point we have two tangents to this circle. So these segments are always equal to each other. This is a well-known property. And so we have here these two segments also equal to each other, and these two segments are equal to each other. So let's denote them by x, y, and z. Okay, so this product of ratios, so let's write it. So like we need to verify that this is equal to 1. If we prove that this is equal to 1 for our case, then these three lines would intersect at a single point. So okay, so let's first rewrite what we have. So we start with b, so we have b TA over TAC multiplied by CTB over TBA multiplied by ATC over TCB. We need to prove that this is equal to 1. So first we can drop the vectors, because we know that all three vertices are located on the sides of the triangle, not on the extensions. So all these vertices all these vectors are in the same, like directed in the same direction. So all these ratios are positive. So, but then we can rewrite these ratios using like x, y, and z. So the first would be y over z multiplied by z over x multiplied by x over y. So I just replaced the segment with x, y, and z, and we see that x and x cancel each other, y and y cancel each other, and z cancel each other, and in total we have exactly 1. So because this is equal to 1, we have by the Chev's theorem. So this implies that by the Chev's theorem, by the Chev's theorem, so ATA, B, TB, and C, TC intersect at a single point. And this is what we needed to prove. Yeah, and this point is called the Gergonne point of the triangle. So this concludes the proof, and that's it for this video.